So normally we can't 3D print plastics and metals at the same time because metals have such a higher melting point. So if you try 3D printing something where you melt the plastic and the metal will catch the plastic on fire. But this limits the uses of new technology we can develop um, very much because plastics can sometimes do stuff that metals can't do. They can be cheaper, they can be easy to recycle. Sometimes metals easy to recycle. They can have more elastic properties than metals can have. Metals can be more conductive, they can be stronger, they can be better heat conductors, while plastics can be insulators. For like wires might be a useful thing. So how can we maybe get around this? Here's a couple ideas I have to get around this. One of the first ideas I have is to use a laser to specifically melt portions of a substance really quickly. And therefore the heat doesn't have time to spread as much to other places. Also, if you can melt a more precise place, then yes, you can get rid of some of the heat to melt other places. Another thing that laser can do is that lasers can melt things using different frequencies of light. Now, some materials absorb light more and heat up more under different types of frequencies of light. So you can also fine tune it that way. And then, if you just heat up a small section, yes, it will heat up the surrounding material. If you do it small enough, when it splits out, when heat splits out, it will not impact the surrounding material much because it spreads out and cools down, kind of. We could also use this to etch away. The laser could also serve other functions too. Etch away features to make it more precise, remelt features to make it smooth out or reshape it, oxidize certain features and do certain chemical reactions to allow for even more customizable control over the whole thing. And laser 3D printers and laser makers and all sorts are getting a lot cheaper. This push will make them even cheaper. We have now laser engravers for under $200 that work pretty well, that can engrave metals and really superheat stuff. We have laser 3D printers around similar costs for resin, some a lot more expensive. There's a lot of things that I'm overgeneralizing here, but there's really fine parameters that we have to talk about. Another thing that can be done is to use laser pulses. And how a laser pulse might work is that if you just pulse heat quickly, then it has more. Then yes, you heat up something really fast. But when it dissipates the heat, it takes longer for the heat to travel around, and most of the heat is lost to air or to surrounding structures. So quick pulses can heat up a specific place very much, and having mobile pulses in short succession can do it very much because that one pulse might heat up a local area 10 degrees Celsius, then it spreads out a little bit. It makes maybe the surrounding area 1 degree Celsius, but then you heat it again. So now it's 9 degrees Celsius, the 1 degree Celsius spread out, and 19 degrees Celsius, but at 1 degree Celsius, it's time to spread out. And if you cool out the surrounding areas with some cooling fan or something, you can contain the heat even more with pulses and cooling around the surrounding areas with specific special designs. You can also use pulses to shift the frequency that the light actually absorbs. So you could have one way of doing that is that hot materials can absorb different wavelengths of light than colder materials, oftentimes slightly different ones. So you can adjust that the pulse first heats up. You see another pulse that's more adjusted. You have that specific material that's hot already. Another way that pulses could help is if the pulse comes from different angles. So it heats up precisely more of a focused area. So where the intersection of the pulses at different times hit is where it heats up mostly. And the area around it, where the laser travel through, has more time to cool down. You could use pulses also just to quickly heat up a material that expands and contracts, and that expansion and contraction itself can force the material to harden quicker and have different properties. Another idea along these lines is to have a what we can call a ceramic layer. And if you 3D print ceramics, which I have made a whole video about, the ceramics can be more insulative and help prevent the metal from contacting the plastics while handling up those high temperatures. And that is a very simple idea. Now, you would have to figure out the best way of making those ceramics, and they still will heat up just a lot slower. Now, if you put out a lot of metal before the ceramic, then you also have a heat sink to some extent, which might cool it down. Another idea that is not as, how would I say it? It will not last as long, is to have ablative abilities. Now, having ablative abilities would work like this, that you 3D print something, and some of the plastic you might purposely have vaporized to keep the rest of the plastic from vaporizing, or have a chemical reaction going on in the plastic that might either completely turn it into gas, or might carbonize it, which is some other thing. Carbonize it when you get rid of some hydrogen and oxygen, you make it more carbon, which can actually make it a useful thermal conductor or material conductor or more of an insulator. It can radically change the properties in good or bad ways. But that gas and stuff emits takes away a lot of the heat, or the ablative, they can have certain chemical reactions actually take away heat, such as melting too, or salt when it gets diluted. So that's for the ablative idea. Now the cons for the ablative idea is obviously that it consumes material, very much so. And another idea is to have it so you program in certain aspects, such as first 3D print certain 3D printed metal parts at the higher temperature, and then around it 3D print the plastic. And that way the time scales are different, so when the metals all cool down, it's only when you put the plastic. Or you can do other ones where you can 3D what parts you 3D print depending on the time. So another way to do it would be if you 3D print an outer casing of plastic, then ceramic, then you 3D print a tiny bit of metal first, and a tiny bit of metal in some parts of it, as where then you print out more metal as you have print out more and more metal, and then metal acts as a heat sink. And you can print faster and faster as you print out more and more of the metal out, and it becomes more and more of a heat sink. You can use combinations of it in complex ways. Combine this with the ablative idea, the pulse idea, the ceramic and laser melter, and play around with a bunch of parameters for both speed and precision to allow for a wide range of objects to be printed. What's more, optimizing such a program will be very, very difficult. I would suggest going on with some heuristics, which are just ideas and general guidelines, you think, then using AI to further refine it, parameters, and see what's possible. It might be also hard to predict what's possible and not possible with this, unlike the engineering approach, because the algorithm might be too complex for a human being to easily understand. Another idea kind of along these lines is just to develop a better insulation. And this can be better ceramic insulations. Ceramic insulations such as sulfur and some mixed with some ceramics can be pretty good thermal insulation. There's also carbon insulations and so on and so on. Or plastics that are just very insulative and you just hope with some of the ablative. On the other hand, besides insulation, you might want to do the opposite and develop a better heat sink in some places to get rid of the heat faster before it reaches other places. And now we're starting to make carbon nanomaterials, which, if they're dense, have some of the highest thermal conductivities. Low density are some of the most insulative. High density have some of the highest thermal conductivities. Another idea is just to design a better overall cooling apparatus. This can be from fans or micro air jets. This can be magnetic cooling locally, but magnetic cooling usually only can cool a couple degrees Celsius fast, but if it's just a nearby material, maybe that's worth it. And then you would have to have what's the material strong magnetic response. It's hard to calculate. You also have laser cooling, which is complicated. We can build it into other lasers maybe. Liquid cooling, we could spray some liquid that evaporates, or spray some liquid over it. Also pros and cons because they might disrupt the actual process. And lastly, we could design better materials. Adding carbon nanomaterials to, for example, to metals can greatly increase the thermal conductivity, and they can also greatly increase the electrical conductivity. This might mean if we added to some material and also strength, we might be able to get rid of some of the problems. Copper and brass. Copper has some of the highest conductivity of any metal. Add carbon nanomaterials, it's even higher. It also gets significantly stronger and better thermal conductivity. Better thermal conductivity means that it can cool down quicker, so you might need to heat up. So if the heat problem becomes less of a problem to heat up other stuff. It also means that maybe because it has better material properties, you can use less of it, which might mean that you have to worry less about heat management and those problems. Also makes it significantly stronger. And if it's significantly stronger, you might be able to replace, for example, steel or other strong metals that have an even higher melting point and are less thermally conductive. Or you could use it to make something like brass or some other metal that has a much lower melting point, a better electrical conductor and thermal conductor, so it works better in the printing stage, and that's also usually less strong. Sometimes stronger, sometimes less strong. Stronger, so you can replace it. That's just one example. Well, thank you very much for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year, 4,000 watch hours, which is really hard. With your help, I think I can do it. Also, I will link some related videos in the audio description. Thank you very much. Goodbye.